Hello, everyone. So for you who don't know me, I'm Ben Shappy, Jason's thesis advisor. I'm going to give the introduction to Jason before he gives his thesis defense. In the introduction, I'm supposed to tell you who Jason is. So let's first start by looking at what he says about himself. This is from the IFO website that he wrote. He mentions things like working on tidal disruption events, getting the NASA Finest Award, and being from Maryland with your horrible, horrible flag. That doesn't tell us very much. So I went to ChatGPT and asked it to help me get a better picture of Jason. And this is what it did. Not entirely sure that helps either. So let's look at his body of work first. He came to us with basically one paper, I think already published or at least submitted, and another paper almost submitted from undergrad, working on various aspects of quasars and AGN outflows. These are the massive black holes at the centers of galaxies and their accretion. When he first started to work with me. My first question was why? My second question was, what do you want to work on? And he basically was interested in nuclear transients and nuclear events. So that's the path we started to go down. The first paper that he worked on with me, I try to have called the Hinkle relation. Jason refuses to name it that. He always calls it the peak luminosity decline relationship, which I find to be much less, it doesn't roll off the tongue quite as well. This is a kind of fundamental relation in tidal disruption events that wasn't recognized before Jason looked at it, and it basically looks at how fast a tidal disruption event declines correlates with how luminous that object itself is. He started to follow up individual interesting tidal disruptions as well. He'll tell you more about these throughout his talk. He has so many papers I'm going to have to go through fast here. He then went and Swift, the spacecraft from NASA, had a calibration issue that they figured out, which then basically affected all nuclear transients because they're hot. He went through and basically did a service to the community as well by basically correcting all the nuclear transients. That paper is reasonably well cited. More tidal disruption events that are possible tidal disruption events. He basically coined a new class of object. So there's tidal disruption events, which are when the star gets ripped apart by a supermassive black hole. Jason will tell you more about that. There's AGN, when there's gas and dust around the central black hole. There's a whole bunch of objects that Jason basically started to find out and piece together that don't really neatly fit in either class. And it's not clear which class they're supposed to belong to. And so Jason coined the term ambiguous nuclear transients. We have Atlas's survey here, their first tidal disruption event. We have a tidal disruption event with another spacecraft from NASA, TESS. We have coronal line emitters. So these are a particularly interesting class of AGN that Jason showed and argued are probably just that they were tidal disruption events that were caught in their late phases by spectroscopic surveys. He wrote this paper in a week while we were at a conference. He even has a solar author paper on the mid-IR echoes. I believe he'll also talk about that today as well. A solar author paper, for those of you who aren't astronomers, for a grad student is exceptionally rare. Another Swift fix, this time for a completely different type of object, superluminous supernovae. We have another interesting tidal disruption event. This is his most recent paper that he submitted, which has basically two peaks, which is quite interesting. This has the second slide. He even has a paper which is about to be accepted, we think, to Science Advances, and that's a particularly difficult journal to get into. And so there's this whole ensemble of work, 13 papers. I don't know why you fell on that particular number. But is Jason really just the science minion? Okay, he is a science minion, but he's not just a science minion. He also is a good advisor. He's worked with a number of undergrads and RUs. Typically, for the RU projects, I make the grad, if they want to work with an RU, I make them propose the project to me. This one was kind of a joint one. Looking at flares, stellar flares, so something, again, completely separate from his typical work, but we worked with a grad student and got a paper on the archive for this. He also worked on AGN in tests with a student who's now at Princeton University as a grad student, Lena. He worked with another grad student in my group, Willem, on another TDE paper. We have more stellar flares this time. This was an interesting combination between Michael Tucker, another grad student of mine at the time, and Jason on this project, looking at stellar flares in the far UV. This paper showed that stellar flares from low mass, basically large flares from low mass stars, actually have extremely high far UV flux, which has implications for the habitability of life around those stars. He won't even talk about this, but Jason did a huge amount of work basically understanding stellar flares to help advise this student. This paper is getting a number of citations as well. And he has two more papers that his RUs from last summer are currently working. So this is a huge ensemble of work that Jason's worked on so far. They say never to show a table and in a talk, but this isn't a talk, so I'm going to show a table anyway. It doesn't actually matter what the numbers are, but these are the faculty. These are statistics for faculty candidates here this time. So these are, some of the best people applying to an R1 institution got on our short list. And if you look carefully, right in the middle, there's a 2025 question mark. That's actually Jason. I put him in the middle. And his metrics are already on par with many faculty candidates at a prestigious institution. So these are not typical numbers. I believe you have the most number of papers from any grad student that's graduated from the IFA so far. He's been a great member of the group. He's really kind of brought the whole group together. This is, I think, our first meeting after the pandemic ended. I think we finally got to see each other in person. And so it's kind of been an extremely good group member, kind of bringing this all together and asking questions about folks. I have a very broad group with people doing lots of different things. So it's typically hard for the students to engage with everyone else. But Jason's done extremely well at that. In Hawaii, I've been told that I know Cookie. I've seen lots of pictures of Cookie. This is his cat. So I've been told upon good authority that he attempts to give Cookie 100 kisses every day. And I think you can see that Cookie seems to be very possessive of him as well, sitting on his clothes. He's also had the normal IFA graduate student adventures to see the observatories. Other adventures as well, some of them that maybe parents and even advisors don't like to necessarily know about, but with hikes around Hawaii. He even was able to survive Michael Tucker's armpit. And he did a lot of outreach as well, not just working with undergrads as well. But this is a video that was made during the pandemic when we couldn't do our normal outreach. And so the grad students got together, a bunch of them, to do basically a video of the solar system. I'm not going to show you the whole thing, but I'll just show you the beginning to kind of give you a flavor.
Hi, I'm Jason.
And I'm Allison. We're grad students at the University of Hawaii Institute for Astronomy.
We're here from Mauna Kea Observatories at Home to give you a walking tour of our solar system.
And so without further ado, I'll give you Jason Hinkle. Just a second.
Thank you so much for that incredibly nice introduction, Ben. I'm happy to be here today to tell you all about my dissertation work over the last several years, which is focused on using optical transients discovered by ground-based sky surveys, in particular nuclear transients, which we believe are powered by accretion onto black holes. And so today I'm going to tell you a bit about their physics, some of the diversity we've uncovered over the past several years, and then how we actually use them to study black holes. It's been nearly There we go. It's been nearly 250 years since the first theoretical study of an object that's so dense, so massive and compact that not even light could escape. In the late 1700s, several philosophers basically asked the question, in at least Newtonian gravity, of what if we set the escape speed of an object to the speed of light? And so these aren't actually black holes in the modern sense, and the idea kind of fell away over time. And it wasn't until Einstein's general relativity and Schwarzschild's exact solution that we got to kind of the current state of black holes. So this is an interesting kind of note of how we've started thinking about these objects. And actually, perhaps most interestingly, even in general relativity, many people, including Einstein himself, thought that this solution was just a mathematical curiosity and that black holes wouldn't actually exist in nature. But it was only a few decades later and some technological advancements that we got our first observational evidence for these black holes. And that came in the early 40s when Carl Seifert got spectra of some very nearby spiral galaxies. And in this case, I'm showing the spectrum of NGC 4151, which is now well known as one of the very early Seifert galaxies. When we look at the central nuclear spectrum of this object, we see that not only there are some lines that you might expect just from star formation in the galaxy, but there are very broad lines, permitted lines of hydrogen and helium that indicate some material moving very, very quickly. And so even at the time, they said, okay, this must mean that there's something that's powering very large velocities, but it wasn't well known what was going on. Of course, now we know that it's material orbiting very close to a black hole. And at least in the history of our understanding of black holes, a big step forward came about 20 years later in the 1960s with the observation of 3C273. So in the intervening time between Seifert and Martin Schmidt, there had been a number of discoveries of radio sources, very compact radio sources, that over time were identified as counterparts to what they thought might be faint blue stars. And when Martin Schmidt went out and took a spectrum of the brightest of these, 3C273, he found that, first of all, it wasn't a star at all, and it also had very strong lines of hydrogen that were redshifted to a redshift of roughly 0.16, which told us that they weren't even in our Milky Way. And so the fact that they were so bright and apparently so distant meant that they were extremely luminous. And the fact that, right, you had this source that appeared stellar in nature told you that it was coming from a very, very compact region. And so we posited that instead of being stars in our Milky Way, these were the centers of external galaxies. It was very quickly realized by other folks that there were other objects that were similar in nature, and that very quickly it was suggested that accretion onto black holes was the most plausible explanation for these. And so Schmidt and others' prediction that these were accreting black holes, of course, was confirmed by the time we had Hubble Space Telescope observations, and there were other evidence earlier, but at least in the case of 3C273, we can see in this optical image on the left that there indeed is this very, very bright central source that's so unresolved and compact that it has these characteristic diffraction spikes that are the signature of unresolved sources. And if you can go look on the right and take a coronagraph and remove out all of this bright light from the center, you see that there is a host galaxy in which this object lives. So this class of objects is known as quasars. They're the most luminous accreting black holes, so luminous, in fact, that they outshine the entire stellar output of their host galaxies. It was rather quickly realized by other folks that if you had these accreting black holes in the universe, you ought to have non-accreting black holes, things that were essentially just living there undetected. And of course, the most famous example is the one in our own Milky Way galaxy, Sagittarius A star. And so on the right, I'm showing some excellent work by the Keck UCLA Galactic Center Group, which have used the Keck telescopes in the infrared and with adaptive optics technology to map out the orbits of stars near our central black hole, telling us, one, that there is a massive object at the position of this white star, and giving us a very precise mass for this object of about 4 million solar masses. And so, of course, this is incredible data, so incredible, in fact, that it won the Nobel Prize a few years ago, but it doesn't work for any other galaxy because these scales that we have to resolve are incredibly small. And even for our nearest neighbor, the Andromeda galaxy, we'd have to start to resolve scales about 100 times smaller. But it's well known now that it's not just our Milky Way and these quasars that have black holes. Essentially, every massive galaxy in our universe hosts a black hole at its center. And it's not only that they host black holes, they seem to be well correlated with the properties of the galaxies. Here I'm showing the well-known M sigma correlation between the mass of the black hole on the x-axis and the velocity dispersion of stars on the in the bulge on the x-axis here. And so this very strong correlation between the two for many orders of magnitude of mass and a large range of velocity dispersion indicates some sort of co-evolutionary process where the black holes in the galaxies know about each other in some way and grow together throughout cosmic time. This seems to be some sort of feedback process in which as you accrete onto the black hole, you launch some sort of outflow or jet that imparts angular momentum and energy feedback into the galaxy and regulates star formation and mass growth in that way. And so through things like this, we know that at least in the local universe, there's evidence for black holes in some sort of link with their host galaxies. But we also now know that there are abundant black holes at high redshift. And in particular, what I'm talking about here is these so-called little red dots from the James Webb Space Telescope. These objects are perhaps unsurprisingly called little red dots because in the JWST images, they appear as very compact red sources. And they're so abundant that in nearly every early image from JWST that was trying to look at the earliest galaxies, understand the galaxy luminosity function at the earliest redshifts, earliest times in the universe, essentially every image had one of these little red dots. So of course, this caused quite a stir, and there was a lot of question as to what was going on with these objects. And by the time we started to get spectroscopic observations, we saw again, like Seyfert saw in the nearby galaxies, very broad lines of hydrogen that are indicative of gas orbiting close to a very massive object. And so now the most well-accepted explanation for these are that they're obscured phase of AGN growth in the early universe. And so combining the local context in which galaxies and black holes know about each other and mapped black holes are abundant, and the fact that we now know that black holes are also quite abundant at high redshifts, we need to actually go out and understand black holes holistically to understand how they impact their growth over cosmic time. And to do that, perhaps the first thing you might think of is, why don't we just go out and take an image of the black hole? And so that's been done after some painstaking effort by the Event Horizon Telescope to essentially use the entire Earth as a radio interferometer. And in doing that, they were able to get images of two black holes, Bovei and M87, which I'm showing here, and then one from Sagittarius A star in our own Milky Way galaxy. These observations are excellent in that by measuring the size of this dark part, the event horizon, you can confirm that the masses that we've estimated through other means are robust, and also that the predictions of general relativity are good, and that we understand the basic theory underpinning black holes. But in general, these are very hard observations, of course, and they don't work for really any other objects that aren't as close. And there's also complications about the intrinsic variability of accretion onto black holes. And so this is something that only gives us a bit of a foundational understanding. So we need to go and do something else to understand more black holes. Perhaps the best understood way to do this is spatially resolving ensembles of stars or gas orbiting in the black hole sphere of influence, which has been done for about 100 or so galaxies in the local volume through things like HST and large aperture telescopes. And here, rather than actually imaging the black hole directly, we're looking at things where the black hole orbiting within the sphere of influence, which is where the black hole's gravity is dominating over the gravity of the rest of stars in the galaxy. And again, these are excellent measurements. They give us very robust masses, allow us to populate these types of correlations I've talked about. But it only works for sources that are either very massive or very nearby or some combination. So we need something else to really go to more distant black holes and up our numbers quite a bit. And the best understood of those are active galactic nuclei, or AGNs, which Ben mentioned a little bit earlier. And these are black holes that are actively accreting. As material falls onto the black holes, it settles into a disk. And as it moves through the disk, viscosity heats it up and it glows very brightly. In many cases, right, we see the bright central cores of nearby galaxies, or in the case of quasars, this is so bright that it outshines the entire galaxy. These are excellent because they're bright. We can see them very far away. It gives us many objects to study, but they're relatively intrinsically rare. They only occur in about 10% of galaxies when we're talking about any sort of accretion onto black holes. If we want to study the strongest AGNs, it's only about 1% or so of galaxies. And so we need something to study the 90+% of black holes in the universe that are otherwise quiescent, and we couldn't see them. And that's where transients, the main focus of my dissertation, comes in. These are events that are transient in the sense that they come and go on human timescales. They are detected by optical sky surveys, and they rise on timescales of about a month or so, and then eventually fade over the next few months to years. And in particular, nuclear transients, these flares that we think are powered by accretion onto black holes, not only one, allow us to identify that there's a black hole in the center where this happened, but if we can understand the physics of these events, we can actually try to use them to probe the properties of the black holes on which they occur. And to date, we have a few hundred of these, perhaps, but as I'll tell you, that's quickly going to blow up in the next few years. And it's really these last two phases of active accretion onto black holes that are most important for understanding black holes, because that's where the mass actually comes from that allows them to grow over cosmic time. And in particular, nuclear transients give us access to this very rare phase of black hole accretion or mode of black hole accretion, the so-called super Eddington accretion. And the Eddington limit I'm showing here is essentially the limit at which you have infalling gravity balanced by outward radiation pressure coming from the accretion onto the black hole. And often in nature, it seems that objects tend to observe this Eddington limit, but there's no limit to the mass that you can dump onto a black hole. And indeed, transients are one of the ways that we can study this phase, which might be incredibly important to actually growing the earliest black holes in the universe. And so for the rest of the talk, I'm going to step through a few broader categories. I'm going to tell you about tidal disruption events, which have been the main focus of my dissertation. I'm going to talk to you a bit about what happens if we have a transient that's in a bit different of an environment than a lot of the TDEs we know so far. What does that do to the observable signatures, and how can we back out some of the information when things are not as we expect? And then once we've talked about the physics of black holes, I'm going to talk a little bit about how we can use them to actually probe, the physics of transients, probe the black holes on which they're occurring. And then I'll close with a bit of future looking towards the next few years of time domain surveys and where nuclear transients fit in. And so to start off, tidal disruption events, or TDEs. So you might ask, of course, what is a TDE? And a TDE is when an unlucky star in the center of a galaxy gets a bit too close to its black hole, and it starts to feel the intense tidal forces stretching it apart. Eventually, it hits this tidal radius where the tidal forces and the self-gravity are equal, and the star gets ripped apart as the tidal forces exceed the self-gravity. About half of that material gets flung out of the system and becomes unbound, but this other half remains bound and slowly falls onto the black hole, powering a luminous flare that we can observe. Some of the earliest theory on what TDEs, at least the fallback of material following a TDE would look like, gave us some key predictions. The first is that the peak fallback rate of material following a tidal disruption event should be well in excess of this Eddington limit I discussed earlier. And following the peak, we should have this characteristic t to the minus 5/3 power law decline, which is one way that we might imagine to be able to select TDEs from other transients in the centers of galaxies. And so taking this forward, people made some predictions on what the events might look like, not just in terms of the fallback, but what would the actual observables be? And if you take this Eddington luminosity, a characteristic scale of the tidal radius for the photosphere, you end up getting out a characteristic effective temperature that peaks in the extreme ultraviolet or soft X-ray. And so the expectation of what we would find for TDEs was these X-ray transients. But surprisingly, many of the first events that were characteristic of TDEs were not in the X-ray, but in the ultraviolet or optical bands. And so here I'm showing an ensemble of TDEs from a recent review by Subi Ghazari. And these objects are interesting in that they actually, even though they're not what we expected, somewhat seem to follow the predictions. They have peak luminosities about at the Eddington limit, which is consistent with Eddington or super Eddington accretion onto the black hole. And they have declines that are pretty well fit by this characteristic t to the minus 5/3 power law. But the fact that we saw these events in the UV and optical rather than the X-ray as we might have expected led to a bit of a question as to where is that emission actually coming from? And so there's broadly two mechanisms that have been proposed for this. That's perhaps that the debris stream after the disruption eventually shocks itself, and that shock powers the luminosity that we see. Or you find a way to very quickly dump the angular momentum in these debris streams and settle into an accretion disk. And in the super Eddington accretion, you often launch outflows. And so you have this X-ray bright disk at the center, basically what people would have expected originally from TDEs. But you also have this reprocessing layer outside of it. And so most of the lines of sight towards this central disk have a large optical depth. And so the X-rays are reprocessed into longer wavelength UV and optical emission. However, owing to a relatively similar energy budget between the two and a lack of directly testable predictions with the observables, it still remains somewhat of a question, at least at the start of my thesis, definitely, of what's actually going on in TDEs. Perhaps we're seeing multiple mechanisms across the population, maybe even in individual events, we're seeing both of these occurring. But there are some trends that we've discovered over the past several years that give us some hints as to what might be going on. First, I'll talk about the broad UV optical emission of these objects, which is where we're getting a lot of insight into most of the emission from these events. Fortunately, in recent years, the Swift telescope has been excellent in following up nearly every TDE that we've discovered from the ground. This is crucial not only to confirming it's a TDE by showing that it's UV bright, but it's given us excellent coverage of their light curves. One of the first things you see is that these events are very luminous and they're relatively smooth over time. But we can look a little bit more closely. One of the things that I noticed early in my thesis was that more luminous TDEs at peak seem to fall off a bit more slowly after their peak luminosity than these less luminous TDEs, the fainter ones, that drop off quite a bit faster. So this is the TDE peak decline luminosity, peak luminosity decline rate relation that Ben referred to earlier. Nothing. If you look at the blackbody radii, the radius of the photosphere of emission that we're seeing, it's quite a bit larger than the tidal radius. And the temperatures are quite a bit cooler. Instead of peaking in the 100,000 Kelvin regime to even 1 million, right, we're seeing something like 20 to 50,000 Kelvin, and the peaking in the far UV. Continuing with this peak luminosity to decline rate relation, one of the things I did early in my thesis was to actually characterize this in more detail, where I showed here on the y-axis is the peak luminosity, and then this decline rate, which is parameterized as the decline at 40 days after peak relative to peak, the amount of the decline in log space. And as you can see, there's this very nice correlation between these two parameters. And so this is potentially related to the fallback of material onto the black holes, but it's also a very interesting way to maybe select TDEs. If we go out and we see a transient in the center of the galaxy, we can measure these two parameters and put it on this diagram. This may be a nice way to actually disentangle different objects. But the story is maybe not so clear. There was some work that Willem did in the past few years that showed that maybe we're not seeing one correlation across the entire sample of TDEs, but perhaps there's some subclasses. Maybe there's this normal group and this faint and fast group that I'll talk about in a minute that don't necessarily behave the same way as the rest of TDE. And so this is somewhat similar maybe to the various subclasses of supernovae where different flavors of physics are causing slightly different observables. But I think right now we don't have enough objects. We simply need to add more to really understand, is this a single correlation? What does it tell us about the physics? Or are these subclasses where maybe we can start to dig a bit deeper? Moving on from the broad UV optical emission of the TDEs, we can also learn quite a bit by looking at their optical spectra. And one of the things that's been well known for a few years now is that TDEs come in a few different classes of spectroscopic types. The most common is objects that show both hydrogen and helium in their spectra. There's also objects that only show hydrogen. There's a few relatively rare class that only show helium. And then recently there was this class of very luminous and also rare classes, objects that essentially show no strong line. They're basically featureless by just a very hot black body. But these classes have also been linked to several other parameters that I've talked about. The objects that show helium in their spectra tend to have smaller blackbody radii, more compact photospheres. The objects with hydrogen only seem to have broader lines. And so there's a suggestion that perhaps what we're seeing for the objects that have helium is that maybe they do have a disk and you're actually getting plenty of flux above the 54 electron volts that you need to power helium-2, whereas the hydrogen-only events might come from something like a collisionally induced outflow, where you're not actually seeing a very luminous disk, but you're seeing the shocks in the material there. And so this potentially suggests that we can use the spectroscopic information of TDEs to understand the physics underlying them. But so far, I've only talked about the UV and optical behavior. I mentioned TDEs should be detected in the X-ray, and indeed we do see that some of them are, but interestingly, only about a third to half of those TDEs selected in the optical, when we go look at them in the X-rays, actually have any significant X-ray behavior. And even for the ones that do show strong X-rays, they essentially never outshine their UV optical emission. On the right, I'm showing a sample of objects detected by the Zwicky transient facility. And on the y-axis is the ratio of this UV optical blackbody luminosity to the X-ray luminosity. And as you can see, essentially all of the events live in this regime that are UV optical dominated. And even sources like this red one that start with essentially no X-ray flux and have this large late time X-ray brightening, even in that phase, they're still only comparable between the two. I should note that there is a class of X-ray selected TDEs that seem to show the opposite behavior. They're effectively only X-ray events, but the rates of those objects are about a factor of 10 lower. And so the large majority of TDEs that we know are dominated by the UV optical emission. So coming back to this idea of the two different emission mechanisms, I don't think we're there yet in terms of definitively saying what's going on, but we have some hints. This disk reprocessing picture is pretty consistent with the idea that only some of the UV optical events, the selected events, should show X-rays, but there is evidence that at least some objects, especially at early times, might have emission powered by shocks. And so there's still work to be done to actually piece together what fraction of objects have which emission mechanism, and is there any temporal behavior where we might see a shift from one mechanism to the other. But I think one of the key ways that we can go forward with this is by studying TDs at the very earliest phases of their emission. And in general, that's very hard to do, right? Because you wouldn't know when a TD goes off. But there is this recent class of repeating partial TDs, or at least repeating partial TDE candidates, that have shown multiple flares. So here I'm showing the object Assassin 22CI, a very long-term light curve, where we see it's essentially doing nothing until we had this one flare that looked essentially just like a normal TDE. We had followed it up like we do for many bright Assassin objects. But then somewhat surprisingly, 2 years later, there was this second flare, which was completely unexpected. And so I'm showing here some other models of what you might expect to see if it is indeed a repeating partial TDE. The idea here is that you have a binary that gets captured by the black hole. One of the stars gets flung out, and the other star is on this highly elliptical orbit that each pericenter passage, it gets very close to the black hole, and some of the outer envelope of the star is ripped off and accretes onto the black hole. And so for this object, we don't see any earlier flares, but we might expect that if it is indeed this case of a bound star that's repeating and coming back to the pericenter and gets disrupted, that we might see another flare. And for this object and a few others, we expect to see them in only a few years. I think for 22CI, it's February 2026. So not even a year from now, we could go and try to see the next flare. And there's some confidence that we can actually go and do this, because this is what Anna Payne did for her thesis here. She studied this repeating partial TDE candidate, Assassin 14KO. This object is quite a bit better for this because it's much more periodic, and we've had many, many flares as opposed to the two that I discussed for Assassin 22CI. But she was able to go and basically actually, when you know when the flare occurs, go look at the object right before it goes off. And so you can see that in these bands, she was able to get data immediately preceding the flare, telling you what was going on right before it, and then get coverage of the very earliest rise to peak. And the models that I've talked about, it's at the earliest times that some of their predictions are the most distinct. And so if we can actually have a sample of objects, I think there's about 5 decently high quality repeating partial TDE candidates, and there's some evidence that we could go out and try to find more. We can start to build a sample of objects with observations at the very earliest times and test the models there, as opposed to waiting to much closer to peak, just when you have to find them, serendipitously. But it's not only the emission mechanism that remains a question for TDEs. There's also this question of, what if we took a TDE, a star getting ripped apart, and put it in a different environment? So far I've talked about kind of normal TDEs, if you will, that seem to mostly occur in relatively gas and dust-free nuclei. And so most of what we're seeing is just set by the debris and the fallback. But if you put more gas and dust in the center, or maybe an AGN disk, you might expect that the observables I've talked about would be drastically different. And we have some evidence of that at low redshift, but it's perhaps even more important to understand this as we go to higher redshifts, because we expect there to be more gas and dust. And here in particular, I'm showing this cosmic star formation rate density as a function of redshift. And as we go towards cosmic noon at a redshift of 2 or so, we see that there's a peak. And as you go to higher star formation rates, this typically means there's more gas. And often when you have more gas, that comes along with more dust. And so as we push to deeper surveys and try to understand these nuclear transients at higher redshifts, we're probably going to have to contend with somewhat different nuclear environments than we've been able to study at low redshift. But as I mentioned, we have some local analogs that can get us a head start into understanding this interplay between observable signatures and the environments in which these objects are occurring. And one of these is this class of corona line emitters. These are events that show strong emission from high ionization potential lines. In fact, they're actually called corona lines because they were first identified in the solar corona, where the temperatures are of order 1,000,000 Kelvin. And so many of these were first discovered in the Sloan Digital Sky Survey as objects that are galaxies, but have these anomalously bright corona lines, but without many of the strong lines that you would expect from typical AGN activity. And so the idea there was that we're seeing some sort of transient event, perhaps, that's very luminous in the extreme ultraviolet and X-ray. And TDs were put forward as an idea, but most of these objects didn't have any real-time follow-up, right? They just had a spectrum, and you had essentially no idea what was happening before or after. Fortunately, though, we've had a number of objects that were detected as transients that then eventually, at some point in their evolution, showed coronal lines. And basically, as Ben mentioned in one of my papers, I went and I actually studied these events and tried to understand, is this idea that they are TDs in gas-rich environments a reasonable idea? And so here I'm showing the color evolution of the mid-infrared light curves of these events from the WISE mission. And so many of these events show mid-infrared flares that are consistent with transient heated dust. So basically what's happening here is you have an event in the middle that's very bright. And if you have dust surrounding it, that dust gets heated up and eventually re-radiates that emission in the mid-infrared. And so on the left, I'm showing the events that were discovered as transients. And prior to their flares, they start with colors that are essentially fully consistent with just star-forming galaxies, which is this blue line here. And after the transient occurs, they quickly get much redder, which is consistent with the transient heated dust. For the events discovered in the Sloan Digital Sky Survey, they start very red, so red, in fact, that maybe you would think that they were AGNs. But as you can see from many of them, they go quickly to these much bluer colors towards this star-forming locus. There are, however, a few events that just sit at red colors and might be more consistent, or likely are more consistent with just being AGNs. And so there is some contamination, but by and large, it seems that these coronal line emitters are transient events. And I was able to place some of them that had particularly good UV optical coverage during the flare on this peak luminosity decline rate diagram that I've already talked about. And as you can see, they lie incredibly close to where the position of TDEs are on this diagram. There's a little bit of scatter, but that might be explained by somewhat more massive black holes for these galaxies, or the fact that you actually have some dust that's obscuring a bit of the emission and making them appear slightly fainter than they might be intrinsically. And I should also note that it's not only that they sit close to this correlation. When you compare to nearly any other class of transient objects, they sit even closer than them. So it's not that we're seeing some other event. It really does seem that these coronal line emitters are TDEs in somewhat different environments, much more gas and dust rich. And so if these are TDEs, we can potentially use them to actually understand TDE physics in a new way. And I think the best way that we can use them to probe TDE emission is by looking at regions that are otherwise unobservable. So in this kind of cartoon diagram of what a TDE broadband emission might look like, you can see in these pink regions, the UV optical and the X-ray, that's where we currently have observations of TDEs. In between, and the extreme ultraviolet and the very soft X-ray, we don't have much data. And that's not for lack of trying. It's just simply that we could never observe any emission from there because it's too readily attenuated by either dust or hydrogen along the line of sight. And so we need some other probe of what's actually going on in that region. And fortunately, we have a number of emission lines with ionization potentials in this region. We have the Balmer and helium-2 lines that I've talked about already, but especially these coronal lines with emission potentials of 100 eV all the way up to a few hundred eV span this region very nicely. And so if you could imagine going and trying to use this, we can reconstruct this unobserved part of the SED. And I've been working with UH undergrad student Athena Engholm for over a year now on this. She's studying this particularly well-studied object from Atlas that shows coronal lines. And what she's been able to do is fit, for each spectrum, simultaneously fit the coronal lines with a simple model like this and try to back out what is the temperature of that black body that powers the coronal line. And as you can see, this is all preliminary work, but she seems to be getting excellent agreement between the temperatures derived from just fitting the coronal lines, which are all in the optical, and the temperatures derived from directly fitting the X-ray spectra for this source. What she's done here is she's scaled the radii, effectively the emitting region of the coronal line gas, up to match the X-rays, and computed the corresponding luminosity. And so in general, it's a pretty good agreement, but what we're actually seeing perhaps is that coronal lines are excellent probes of otherwise obscured X-ray emission, right? At early times, we see only upper limits. Effectively, the source appears to be undetected in the X-rays. But the fact that we see coronal lines at this early time tells us that that can't be the case. There must be X-rays powering these lines. And so what we're perhaps seeing is that the region towards the center of the black hole has a very high optical depth to the X-rays, but not nearly as high to these coronal lines that are coming out in the optical. And so we can imagine using them to study the intrinsic X-ray emissions of sources where they might have a time variable X-ray emission that's not only from intrinsic X-ray variability and accretion rate changes, but also obscuration changes. And so this is just one object, but we have a number of other objects that are potentially amenable to this. And this also tells us that when we find objects with coronal lines, we need to go follow them up and get a nice spectroscopic coverage so we can play a similar game with the larger sample. I've also spent a lot of time in my thesis studying these ambiguous nuclear transients, or ANTs, which, as Ben mentioned, are these objects that sit somewhere in between AGN flares and TDE. On the right, I'm showing one of the best studied ones, the Assassin 20HX. And what we see for these events is that in the ultraviolet and optical here, they're very well fit by black bodies, which is a typical characteristic of TDE emission. In the X-ray, however, they're quite a bit different as compared to the third or half of TDEs that only the third or half of optically selected TDEs that show X-rays. Nearly all of the ANTs show X-ray emission. And it's not very soft like we see in TDEs. It's quite a bit harder. It actually has a power law like X-ray spectrum with photon indices of about 2 or so, which is much more consistent with an AGN-like picture. So perhaps that's indicating that we're seeing some sort of transient in an AGN host galaxy where you have the AGN environment that is changing the emission. And this type of picture is consistent with the kind of rough rates that we're seeing for ANTs. Sky surveys have now found about 10 to 20 or so reasonable candidates for ANTs, which is of order 10% of the total TDE rate. And so just, obviously these are rough numbers, but taking the roughly 10% of galaxies that host AGNs and multiplying that by the TDE rate, if these ANTs are TDEs and AGN host galaxies, we'd expect it to be about this rate. And so that's some evidence perhaps that these ANTs are powered by TDEs. But there's perhaps other evidence that we should take into account. And of course, we want to look at their spectra. In terms of their continuum emission, they're quite similar to TDEs. It's very blue, tells us that there's some sort of hot emission peaking out in the ultraviolet. They're quite a bit different in other ways, though. They have very strong emission lines from hydrogen and other forbidden lines that are consistent with long-term AGN activity, or at least higher star formation rates in the host galaxy. But they do have broad lines in some cases, like this helium-2 here, that are indicative of some sort of high energy emission coming from the central source, indeed telling us that these are probably powered by accretion onto black holes, and not some strange class of supernovae or other type of transient. The picture of having material near the black hole for these ANTs is supported by some evidence in the mid-infrared. Nearly all of the ANTs that we know to date show a large mid-infrared flare consistent with this infrared echo of transient heated dust. When we look at their covering fraction, which here I'm calculating as the peak luminosity in the infrared relative to the peak optical luminosity, we see that they have covering fractions of order 10 to 30%, which are much higher than the roughly 1% in most TDE hosts. I mentioned that TDE hosts are relatively gas and dust free. That's consistent with the lack of infrared echoes for most of the events. But the ANTs are quite different. And if we actually compare to the typical trend of AGNs in terms of their covering fraction with black hole mass, we see that the ANTs are quite similar. And so this seems to suggest that perhaps we're seeing a transient that's occurring in an AGN host galaxy. Maybe this is the AGN Taurus, whether that's an active AGN or a recently turned off AGN. I think this is a pretty clear indicator that we have dust that's very similar to an AGN geometry. There's also a nice similarity to some other TDEs like those selected in the mid-infrared. Basically here, you're trying to look at events that show mid-infrared flares. And you're essentially agnostic to exactly what's going on. You just need something that's high energy in the center of a galaxy. And the covering fractions here are quite similar. And so I think it's interesting to think that we could potentially use ANTs to try to understand the broad range of flares that are only seen in the mid-infrared and lack multi-wavelength counterparts in many cases. In addition to ANTs, I've recently studied this class of extreme nuclear transients, which are interesting in that they're quite a bit more luminous and long-lived than nearly any transient that we've known. These are the events shown in red up here, with luminosities well in excess of typical TDEs, which live down here, and most supernovae, which are living at the bottom of the plot, not even shown here. And the fact that they're both luminous and very long-lived means that they're very energetic. In fact, they're so energetic that they're the similar energy to about 100 typical supernovae. So that's crazy, right? How would you get that type of energy out of an object? It almost certainly means that they're powered by accretion, since that's the most efficient way we know of converting mass into energy in the universe. And when we go through the mass calculation from host galaxy scalings and look at the energetics and timescales, they seem very consistent with being powered by more massive star TDE. When we look at their black body properties, we see, of course, that they're more luminous and long-lived. I already said that. But when we look at the radii and temperature, they fall very nicely into this idea that perhaps they're like scaled up ants, right? They're occurring in somewhat more gas and dust-rich environments than normal TDEs, but they are quite hot, much hotter than typical supernovae, and they don't cool over time. Whereas supernovae have this expanding ejecta that eventually cools, these ants and Ents all seem to sit at a relatively constant temperature throughout their emission. The spectra also agree with this picture of effectively a scaled up ant, where we see that these red spectra up here, again, have blue continua and broad lines consistent with accretion onto black holes. They also don't have any absorption lines, or these broad absorption lines that would tell you that they're supernovae. And in the paper, we went through many different potential physical scenarios and eventually settled on the fact that these are probably the tidal disruption of either somewhere in the neighborhood of 3 to 10 solar mass stars. And that's also supported by this seeming continuum between the most luminous ambiguous nuclear transients and the extreme nuclear transients I've studied. So here I'm showing the energy of an event versus the peak absolute magnitude. And we can see that there's a very nice correlation between the ants and the Ents, and they're all much more energetic than these AGN flares from the Catalina real-time transient survey that also seem to have quite a bit more scatter in their the trend here. And so the fact that we're seeing this pretty tight correlation between the two seems to suggest that there is some continuum, and that maybe these are all powered by tidal disruption events, and the ones that are the least luminous and energetic are simply less massive stars, maybe a few solar masses, all the way up to the most energetic events that are probably the disruption of order 10 solar mass stars. And so if these are all TDEs, the various classes I talked about, we can actually go and try to probe the black holes that are on which they're occurring. And to set the stage for that, I want to bring up this nice diagram from Yuhan Yao and her work with the ZTF TDE sample. And this diagram shows the rate of TDEs as a function of the mass on which they occur. And perhaps the most important thing that allows us to actually even use TDEs as a probe of black holes is the fact that the fallback timescale of a TDE, basically the timescale on which the TDE should decay, scales with the square root of the black hole mass. And so in principle, you can use TDEs with different timescales to isolate different parts of this mass spectrum. And so if we say wanted to look at the lowest mass black holes, we would go to faster events. And there is this relatively well-studied class of faint and fast TDEs that, as the name implies, are intrinsically faint. And this is coming from the fact that if they're lower mass black holes, the Eddington limit is lower, and so their peak luminosity should be quite a bit lower. And they're also quite a bit faster declining than many of the events living here. I already talked about the luminosity decline rate. But with these events, we can go and try to study the lowest mass black holes, and indeed go off the left side of this diagram and try to study intermediate mass black holes, understand, do intermediate mass black holes exist? How common are they? And things like that. And that's actually, in my thesis, I was able to study one of these objects very well, Atlas 18 MLW, which is a bit of a success story for the spectroscopic classification of astronomical transients survey, which was led by Michael Tucker during his thesis. And this object was actually observed quite early in SCAT's operation, but wasn't classified at the time until Michael went back through much of the early data and re-reduced it. And we found that, hey, this object has a very blue continuum. It has a broad line that's presumably H alpha. And so we said, this is probably a TDE. And so we went and we got the available light curve data from existing ground-based surveys. Right? We didn't know in real time what this event was. It wasn't classified. And so there was no follow-up for this event. We simply had to have the one spectrum and the light curves that existed. But even with that, we were still able to measure peak luminosity and decline rate for this event and show that it sits nicely on this trend between peak luminosity and decline rate, telling us that this probably was a faint and fast TDE. And the reason that this object in this study was important is that as we go to next generation surveys, like the Legacy Survey of Space and Time on the Vera Rubin Observatory, we're going to find many, many of these faint and fast TDEs. These are the most intrinsically common type of tidal disruption events, perhaps 1,000 a year or so that LSST is sensitive to. And so like many of the transients in LSST, Assassin 18 MLW had very sparse data during the event. But even so, we were still able to classify it as a TDE and be able to put it into the sample. And so we're going to need to use some of the similar tricks to be able to play a similar game with many of the transients from LSST. It's also important to study transients occurring on the lowest mass black holes because they're very important to understanding black hole seeding mechanisms. I don't want you to pay too much attention to any of the details on the left, just the fact that the number of black holes of a given mass, the black hole fraction as a function of galaxy mass, and the relationship between black hole and galaxy mass are sensitive to black hole seeding mechanisms in the early universe. And for many of the black holes out there that are currently quiescent, we need something like faint and fast TDEs to actually go out and probe the black holes that are living in these low mass galaxies, these low mass black holes. It's not only TDEs, though, that are relevant. We also know that AGNs can occur in low mass galaxies. And I've been fortunate to work with some excellent RU students like Nina Triber, who studied AGNs and TESS. In particular, here I'm showing a known dwarf galaxy. I'm somewhat cherry picking a well-known example to show that there is variability consistent with an AGN, and it occurs on a short timescale, which is what you would expect for AGNs of low mass. I recently worked with Ashley Tarrant, who's an undergrad at OSU, and she did an excellent job studying this known correlation between black hole mass and timescale. And so this, of course, not only tells you that if you want to look for low mass black holes, you should look at low timescales, but if we have a light curve like this, and you can robustly model the light curve and measure its timescale, you can plop it down on this diagram and get a quite robust mass out of it. And so this also, of course, allows us to study black holes of lowest mass in the smaller fraction that are accreting, but a nice complementary probe to the many faint and fast TDEs that we expect to find. On the other end of the mass spectrum, if we wanted to study very massive black holes, we need to look at things with very long timescales. And I've already kind of given this one away. It's the extreme nuclear transients that have very high peak luminosities and long timescales. But one of the most exciting parts of ENTS for studying black holes is the fact that they're very luminous and long-lived. That means that they're going to be visible in surveys for quite a long time. And so we're going to be able to expect a large number. And the fact that they're luminous means that we can see them quite far away. So in LSST, given the currently known ENTs and projecting that out, we might be able to see them out to a redshift of 2 or 3 or so. And in Roman, we can see the redshifted light all the way maybe out to redshifts of 4 to 6. So getting out to the regimes where we're seeing black holes accreting in the early universe, where there's quasars that seem very massive. And now we have a new avenue to study the other black holes that exist out there that previously were essentially undetectable. And so that's going to allow us to push beyond where we currently have TDEs covering black holes up to very high masses. And you might see that this falls off here, and that's actually because TDEs of roughly solar mass get disrupted inside the event horizon. And so we could never really probe the highest mass black holes with the typical TDEs. So we need more massive stars like the ones that we think are powering these ENTs to actually probe the highest mass black holes. So I've talked a ton about black holes so far, but as Ben alluded to earlier, that's by far not the only thing I've done during my PhD. I've been lucky to work with excellent RU students, Vera Berger and Jess Seldes on stellar flares. I used TESS for something that it was certainly not designed for, to go look at extragalactic sources, not transiting exoplanets. I studied superluminous supernovae, a very different type of luminous and energetic events. And I was recently successful in a HST bridge program to step a little bit more into the galaxy evolution side and understand galaxies that have this extended O3 emission that might be powered by TDEs, or at least understanding the interplay between AGNs and TDEs in post-starburst galaxies. And so finally, I'd like to take a little bit of a look towards the future. I'm going to bring back this diagram that I've shown quite a few times at this point and remind you, right, that faint and fast TDEs are probes of low mass black holes. Extreme nuclear transients are probes of high mass black holes. But what I haven't hinted at or really dug into is the numbers that we expect to see. Right, on the faint and fast side, upcoming surveys like LSST and Ultrasat in the UV are going to take the roughly 10 that we know now and quickly explode this number to many hundreds to thousands by the end of these missions. On the extreme nuclear transient side, things like LSST and Roman are going to take the 3 that we know now and go to hopefully at least 100. So not only on both sides of this mass spectrum do we have an increase of roughly 2 orders of magnitude which is going to give us better statistics on black holes, we might also be able to start to dig into the diversity of these objects and understand their physics quite a bit better. The UV spectra of these objects are also relatively poorly understood. I mentioned that they're hot events, they're dominated by their UV emission, but we don't actually understand too much about their spectra. And that's because getting UV spectra is quite hard, right? Basically, only the Hubble Space Telescope can do this. So far, there's only been a handful of published 2D UV spectra, and the diversity has made it difficult to understand any connection between the events and what we see. But there's about 40 spectra of 15 different objects that are just sitting on the HST archive waiting to be analyzed. That's something I've looked into a little bit, but it's a difficult problem. It's going to take some time to think through. But there's also the ants that I've talked about. And I was fortunately recently successful in an HST program over the next few cycles to get spectra of several new ants to be able to understand their emission in the UV and try to tease out this question of, are they actually the TDEs and AGN environments that we think they might be? But in any case, the UV spectra of these objects are incredibly important to understand at low redshift, because as we go to higher redshift, in the optical and the infrared, we're going to start seeing the redshifted UV light. And so we need to understand the local analogs in the UV to be able to understand the emission of these high redshift objects that we're going to see. I mentioned Ashley's work already, but if you kind of go through the exercise of this timescale and mass diagram, you can basically see that even with existing surveys like Assassin or upcoming surveys like LSSC and many surveys in between, we're already sensitive to a wide range of black holes of different masses living in AGNs. And combining these existing surveys and upcoming surveys, all of the light curves for these AGNs essentially exist. And all you need to do is model them, and you get black hole masses out for free. Finally, I've talked a bit about super Eddington accretion, but I think there's an interesting opportunity for us as a field to basically connect the low and high redshift ends of black hole accretion. Both for low redshift TDEs and for higher redshift AGNs, it seems that super Eddington accretion is important. And when you have super Eddington accretion onto the black hole, instead of a thin disk, like I discussed earlier and many of you are probably familiar with, you have extra radiation pressure that tends to puff up the disk. You get a very thick, almost funnel-like geometry. So that changes some of the observables, in particular, makes your X-ray spectra quite a bit softer. But as I said, especially at high redshift, it seems that super Eddington accretion may be very important to growing black holes quickly and getting to the point that we have massive black holes very early in the universe. So I think there's an excellent opportunity to have some feedback between the two and apply things that we've learned at low redshift from TDs to higher redshifts and vice versa. I just want to take a step back before I close and say that everything I've talked about today about black holes is occurring in a very, very small region at the center of the galaxy. So small, in fact, that this box is drastically oversized. But as I said, there's quite an intimate relationship between the black hole and their galaxies. And so if we want to understand all of the mass growth, both stellar and black hole in the universe, we really need to pay attention to these black holes. As I said, most of the black holes in the universe at any given time are quiescent. And so I hope that I convince you today that transients like TDEs and the other slew of related ones are our best way towards studying black holes at large. Before I close, I just want to take some time to thank all of the many people that made this possible over the last few years. First, I want to thank those of you who have served on my committee, especially Ben, for being an excellent advisor. I've, as you've seen, both through his presentation and mine, done quite a bit in this thesis, and that's in no small part to the fact that he's always been very willing to read my proposals, whether or not they were successful, to decide to co-advise students with me, which is a lot of time and effort. And so that's helped me grow tremendously. I want to thank my undergrad advisors who have set me up for success in terms of research early on. Thank many of the people in Assassin, which has been an excellent collaboration and given me so many opportunities. They've been excellent collaborators, and I've learned so much from them. Similarly, I've learned a ton and made great friends with many of the people in Ben's group and gotten a ton of SCAT data that has supported this thesis. I obviously want to thank all of the excellent students that I've had the privilege to advise over the years. They've taught me a lot and made me a better scientist and advisor through working with them. I collected a lot of data from Mauna Kea observatories over the years, so I would be remiss if I didn't thank the many staff and people that make that possible. Similarly, many folks at the IFA that make things work, make sure that I can get paid, support the grants that I've been successful in getting. have helped with technology, including setting up the dissertation today. As Ben mentioned, I've been involved in outreach, so I'd like to thank the folks that make that effort possible and support students in working with outreach. I want to thank my incoming cohort, who I went through classes with and had my first days as a grad student at the IFA with. The many people I lived with throughout the years, my roommates, the many friends that I've made over the years. They've been excellent support outside of research and sometimes forcing me to take a break from research and do other things. I want to thank my family for all their love and support, especially the folks that have been able to be here to celebrate with me today. My mom, my dad, my sister Jessie, my grandma, my stepdad Rick, stepsister Melissa, soon to be stepmom Annie, and many others who aren't here, especially my grandpa Poppy, who I know would have loved to be here. And then finally, last but not least, I have to thank the people that I spend most of my days with, my partner Alexa and my cat Cookie, who certainly keep my life interesting, but also full of a lot of love. And so with that, I'm very happy to put up my summary and take any questions.
How our dissertations work is that now we'll take questions first in person and then online, starting with non-committee members. After those questions are done, we'll excuse everyone except the committee, and then we'll have a closed door session where committee members are allowed to ask questions. So I'll first ask if there's any questions in person. Okay.
Maybe a fairly simple and naive question, but why are not more TDs periodic? So you showed a couple, the one that Anna studied and the one that you studied. Do we actually know how many are periodic? And if we do, it seems to me like the fraction is not very high. So why is that? If it's stars going around the black hole getting disrupted, it should happen more regularly.
Yeah, so most of the way that we get TDs is through two-body interactions. And so a lot of these are actually coming from the outer regions of a nuclear star cluster that simply interact and get sent in on plunging orbits. And so we expect that a lot of the TDs that we'll see are full disruptions. And that's actually probably mostly because they're more luminous. As a function of rate, you probably do see more partial disruptions, so things that only get partially stripped, but they tend to be less luminous. But these are still different than these repeating events, right? The repeating ones, at least we think, come from Hill's capture of tight binaries in the galactic center. And so there's only a relatively small parameter space where you have a binary that's massive enough and close enough that it's hard enough relative to the velocity dispersion to actually live a long enough time. And not only does that have to be the case, but then you still have to kick it in to the center of the galaxy and have it ripped apart. Right, at that point, you then have potentially a star that's orbiting, but it's still a question as to what actually happens to that star over time. And does it ever actually get onto an orbit where you would have a material getting stripped off? And so I would say theoretically, the rate is not particularly well understood. It's something that maybe I'm hoping to do over the summer here is understand a little bit about this type of evolution. But maybe on the observational side, we're actually finding quite a bit more of these repeating partial TDs, especially recently, than we might have expected. The rate is kind of going through the roof from Anna's 14KO, which I think her first paper was in 2021, which is probably the first event. And now I think we have maybe 10 claimed partial TDs. And so the fraction might be a lot higher than we would have.
And it should scale as a function of the luminosity of the TDs, so that the less luminous ones are the more extreme ones you should expect to have to change.
So in general, yes, the partial TDs should be less luminous. And so you might expect, sorry. That's my bad. Okay, here. So what I'm showing is in these models, you expect the evolution to be such that at early times, you're only stripping off a little bit of the star. And so the flares are relatively faint. And over time, they should get progressively deeper and deeper, and they should be more luminous. And so there is some concern perhaps that, for at least some of the events that are close to the detection threshold, that there could have been earlier TDs that we just simply didn't detect. Right, in this case, we seem to have ruled that out for the existing models, but the entire field is relatively new. So both on the theory and observation side, there's still a lot of work to be done to really understand what we're dealing with. Did that answer the second part? Okay. Goldie?
You really great talk, by the way. Obviously. You're talking about opacity for X-ray luminosity relative to longer wavelength stuff. Could you comment on if there's some sense of what physical environment is going to be, like what you can infer about the physics of the particular system or the TDE because of that opacity?
You're talking about this type of thing that I was
Yeah.
mentioning? Okay.
Yeah.
Yeah, so I mean, I think I should admit that all of the understanding of the physics of these coronal lines is relatively new. We know that there needs to be dense gas, but there's still quite a bit on the photoionization physics side to really robustly say what we're, to take these measurements and go to the SED constraint. But the bigger thing is that we know that even for a modest extinction in the UV optical, right, these lines are in the optical range, and so they're extincted at, if we have an AV of a few or one, the X-ray opacity from a typical ISM gas to dust ratio, the X-rays are getting obscured by the gas rather than the dust that's obscuring the optical. And that tends to lead to much higher opacity. And so you could have a case where the X-ray opacity to the center of the galaxy is much higher than the optical. I don't know if that fully answers the question, but I think there's more work to actually understand, what are the properties of the X-rays and the coronal lines, right? There's only a few where we even have enough data to start to put them together and understand the interplay between them. And once we have that, we can try to actually go back to the physics, but I think there's other work to do first.
With the much larger volumes probed by Roman and Rubin, is there a possibility of detecting more than one TDE from the same galaxy?
In principle, sure, but the rate of TDEs in an individual galaxy is typically of order, 1 per every 10 to 100,000 years per galaxy. And so there are some ways to increase this, perhaps through, more steeper nuclear density profiles. Maybe you've had a merger or something that drives a bunch of gas into the center and mixes up the stellar orbits. But in general, it seems unlikely that we would see multiple TDEs from an individual galaxy within a short period of time. The other thing to remember, right, is the redshift expands the time. So in the rest frame time that we're observing here is even shorter as you go to high redshift. Maybe we'll see some of the repeating events, but it's likely that if you see, something that has seemingly 2 TDs on short timescale, rather than being 2, separate stars getting disrupted, it's probably the same star getting partially disrupted.
If you could detect, if you were lucky enough to see 2 distinct TDE events in the same galaxy, is there something you could learn that would be distinct from what you're learning right now, just from 1 TDE per galaxy?
It would be nice in that it's the same black hole, and so in principle some things might be the same, but the problem is you are sending stars in at very different angles relative to the black hole spin. We think it's likely that most massive black holes have non-zero spin, and the way that you approach the black hole changes how a TDE looks. Basically, if you approach in the prograde direction, you can be disrupted much farther in. Retrograde is the opposite, and that changes how the material falls onto the black hole. And so the concern, I think, would be is even if the mass of the black hole is the same, your actual impact parameter relative to the black hole is effectively random, at least for the TDs I talked about that are coming from the edge of the star cluster. And so I think it's a good idea and something that's worth thinking about, but I worry that there's other confounding variables that make it not as easy as you might want that to be. Dan.
How much would you expect the spectrum of the TDE to change as a function of the star, like a more evolved star, that affects the spectrum?
That's a great question. Especially for evolved stars, you would expect that they get disrupted somewhat farther away and they have weaker interactions. And so for an evolved star, likely you're only stripping the envelope as compared to, these are presumably all full TDEs. And so you're seeing a mix of material from the envelope all the way through the core. In fact, there's some TDEs that have, at least in the ultraviolet, very strong nitrogen lines that indicate some like CNO process material. But in the case of an evolved star, if you're only disrupting the envelope, perhaps it might be dominated by hydrogen. Of course, you have mixing that might change that. But to date, we don't really have any particularly strong evidence for TDEs of evolved stars. They tend to be very low luminosity and over many year timescales. So I did look in my time here, but we were unsuccessful. And there's also potential concerns that they might not even be as luminous as simple predictions of the fallback onto the black hole. But certainly you're right that if you could imagine a star where you just gave it some arbitrarily strange, chemical composition, that you might expect this to be different. But that's just basically saying, what is the material falling onto the black hole? There's the entire side of the actual radiation transport physics that is still relatively understudied for TDs. I know Brenna Mockler was just recently here giving a job talk, and she's one of the people that's really trying to push hard on actually taking fallback and sending that all the way through radiation transport to what the spectra are.
Yeah, with the discovery of these subclasses of TDEs, how is our picture of the population of TDE host galaxies evolved?
Yeah, as far as I'm aware, the faint and fast TDs follow the general trend of TD host galaxies. There are some that are in post-starburst. So the general picture of TD host galaxies is that they're more centrally compact than a normal galaxy, which perhaps follows from the fact that that should lead to more stars getting sent into the middle of the galaxy. And post-starburst galaxies as TD hosts are overrepresented. That's not to say that TDs don't occur in other galaxies, but that's the predominant mechanism. Of course, there are some selection effects that you have to care about. If there's too much gas and dust, or especially dust, right, you wouldn't actually see them. But as far as I know, there is no strong distinction between some of these. I'm not necessarily saying this is a true subclass, right? There's just suggestion, but these seem to follow the general trend. But as I said, right, with upcoming surveys, we're going to find many, many more. And as long as we're reasonably confident that they're TDEs, and there's a bunch of efforts to actually classify TDEs photometrically, of course, we can go out and do galaxy statistics on a much, much larger scale than the 100 or so we have now, going out to thousands, and ask that question.
So that star in our galaxy that's on a really eccentric orbit, what's the expectation time for?
Oh, that's a good question. I don't actually know the time scale, but I do know that the pericenter of that star is still quite a bit away from the total disruption radius. And so a star like that on its own wouldn't get disrupted unless it was either kicked in or evolved to such a large orbit, large stellar radius that it might get disrupted. Right. In general, the TDs that we are thinking about are coming from a completely different mechanism. But it is interesting to think about the center of the galaxy, especially in the context of Hill's capture and things like that, to understand, what is the observed population of stars near the center of the galaxy that has connections to extreme mass ratio in spirals and things like we would care about, for this repeating partial TDE case.
There is a rate at which it's angular momentum getting kicked that
Sure.
At the center.
Mm-hmm.
So sooner or later, there's going to go close enough.
Yeah, that's fair. I don't know the time scale off the top of my head for that expectation.
Okay, last question in the room, Will.
You've spent a lot of time talking about TDEs and their environments. How well do we understand the pre-TDE environments from existing surveys? And is this something that, in addition to providing us many more TDEs to study, will upcoming missions also help us better understand pre-TDE environment as well?
So in general, the problem for a lot of the TDEs, right, is that there doesn't seem to be anything going on in the centers of galaxies. And so it's very hard for us to really study. We've made some attempts, showed this long-term light curve here to basically understand, is there variability before the flare? This is some of the work that I did with TESS to essentially understand, are there AGNs in these galaxies? But quickly, as you go to lower Eddington ratios, even if you have accretion onto a black hole, you wouldn't necessarily expect there to be much variability. Now, as we go to deeper surveys, right, the fractional variability that we can probe gets much better. And so we can start to do that on a much broader scale at lower, much better sensitivities and understand the AGN fraction. There's also, of course, upcoming radio surveys and things like that. And lower luminosity AGNs tend to have radio emission. And so we can potentially try to understand, the population of lower luminosity AGNs that are TDE hosts. But of course, there's also the many things that we know live in AGN environments. And I think there it's really just understanding the sample better and having deeper data, better multi-wavelength coverage will really allow us to understand exactly what's going on in the centers of galaxies that eventually host TDEs.
Questions online? I believe you can raise your hand. Let's go to Esther.
Yeah. great talk, and I'm wondering if you can also talk a little bit about the prospects of future UV missions, not just as follow-ups of things, like, for example, Dan's question about looking for specific features, but since so much of what you're seeing comes from features that would be in the UV, what are the prospects about going in different directions and finding things out in the near future?
Yeah, so I think from just the photometric side, we're going to have ultrasat that's coming online in the next few years. So that's going to be sensitive to the UV emission of many TDEs. It's also potentially going to tell us if there's other classes of objects that are consistent with TDEs that don't necessarily look like what we have so far. But there's also upcoming missions like UVEX that will have both survey and spectroscopic abilities. And so I talked about the UV spectra. And one of the things I hope to do over the next few years is understand the UV spectra better. And so as we have a little bit more understanding there, we can go to future surveys and start to understand the broader population of TDEs in the UV. I mean, there's always the possibility, right, as any new deeper survey turns on or something in a new wavelength regime, we tend to find unexpected things. And so I think that's likely as we go forward too, that there's going to be things that are new and different. And so what I'm really proposing here is that we take what we know now, we build a very strong understanding of the existing sample, and then we can place new events in context relative to that as we go forward.
Awesome. Thank you guys so much. I don't see any other questions online, so let's thank Jason one more time.